Hi, today I'd like to talk to you about symbolic specialization. I find there are a lot of people that are not fully aware of the benefits that symbolic techniques can bring to their applications. And here's an example of how you can make code run faster. So first off, when you're writing code, you don't just start with writing code. I come from an engineering background, so when I think about this, I think about how you start off writing out the equations for your system, and you describe how your system behaves. And you define a problem that you need to solve. You work out the steps to that problem in an algorithm, and then you translate that algorithm into code, which would then get compiled and run on a processor. So there's really a lot of steps here. And when you look at implementing those algorithms, there are really two main camps that those techniques can fall into. You're either looking at numeric methods or symbolic methods. Now, the numeric methods are very widely used in engineering and science communities. And really what they do is they define how numbers are going to flow through the different operations defined in your algorithm. Symbolic methods are a little different. So you see them used more in specialty applications. You see sparse linear algebra libraries use them a lot, and compiler analyses and optimizations are two prime examples. And in this case, the algorithm builds an expression for the answer. So you could have expressions like a times sine b in your algorithm at one point, and you can keep working with that expression without having numeric values for a and for b. And you can keep doing transformations on it, and you can understand what your solution will look like. And using Maple, you can generate code from those expressions. So there is an application example that we were working on recently with a customer, and I don't want to get too bogged down in the details of that application because that's more for another webinar. But what you have here is a scalar function that they were trying to minimize. So we have this f of x with lots of variables. In this case, there are 60 of them. And so to do the minimization, you end up having to take the second derivative of that function f. When we do that symbolically, we know what the derivative is going to look like. So we can form this k matrix as the second derivatives of f, and we can see that it has a lot of really rich structure. So there are lots of zeros in this matrix. And the matrix can be broken down into some subcomponents. So we have H and G submatrices here. And then for their application, they had to solve linear systems involving a matrix like this. And there's a special technique you can use called the Null-space method. So again, I don't want to get too bogged down in the details of this, but there's a reference down here for those of you that might be interested. But really what's important here is that you start off with forming that Hessian matrix K as the second derivatives of f. And then you're doing a matrix factorization of G, that submatrix. And that gives you a matrix Z. And so we can figure out what the sparsity pattern of Z looks like, again using symbolic techniques. And then there's this multiplication here in step 3. So they form a matrix E as the product of Z transpose times H times Z. And so for this particular algorithm, when they implemented it, when our customers implemented it and tried it in practice, they found that this matrix multiplication step was very expensive and very slow. So they want to know what they could do to speed it up. So I started looking around at how you can do this in different ways. And what we found is that symbolic specialization really helps speed this up for our client. And so what is symbolic specialization? You're using your problem knowledge to generate code that is specific to this problem. So we're going to generate code specific for that multiplication. Basically, if you have a generic controller, I say controller here because it was a model predictive control example, generating generic code is inefficient. So what we can do is we can make a controller that's specialized to this car, to this automotive application. So it doesn't have to be able to handle any car, it just has to be able to handle this one. So this is the kind of pattern that you see a lot in science and engineering, where you do lots of analysis up front on code that you're going to run a lot of times later. So we use symbolics to give us those matrix patterns that I was showing, And then we can use symbolic techniques again to leverage those irregular sparsity patterns automatically. So you don't have to know what kind of matrix you have, what special category it might fit into, so that you can choose what the best matrix multiplication technique would be. It could be a completely irregular, random looking sparsity pattern, and the symbolic techniques will be able to pick up on that and get you faster code using that knowledge. So if you break down the multiplication, it's kind of interesting to look at. So this figure is best read from right to left. So we start off with h times z, and that gives us an intermediate matrix T. And then we do T times Z transpose, and that gets you your final matrix E. And that's the one we're really trying to compute in that third step of the algorithm. So you can see E is actually completely dense by the time we finish the multiplications. So we start off with a good deal of sparsity, and T gets a little bit more dense, but then by the time you get the final result, it is completely dense. So I thought it was really interesting to see how, even if your answer is dense, as long as you start with some sparsity, these symbolic techniques can help you. So what I wanted to do is compare different ways of doing this multiplication. So there's a few methods that I looked at here. One is just a triple for loop. I tried unrolling those for loops so that the compiler could do more optimizations. And I looked at two sparse linear algebra libraries, Sparse and Eigen. And then finally, I used Maple to generate symbolically specialized code for this application. And then to compare them, I looked at three different metrics: the runtime, the memory usage, and the compiled object file size. So this gives us a good idea of what the trade-offs are between the algorithms. So with the triple for loop, this is something that you'd see in a typical numeric library, and you have 3 for loops that's going to be doing lots of additions and multiplications within them. And it's very generic. The size of the matrices are left as parameters. And so this is probably how you would learn to do matrix multiplication at a university course, in an introductory course. The next version is an unrolled for loop. So if you take those for loops that we had before, and you know what size your matrix is going to be ahead of time, you can get rid of the for loops by just unrolling them. So you're basically expanding all of those different operations that you're going to be doing. So you save the overhead of having to increment a counter variable and having to do lots of if checks to see if you're at the end of your loop yet or not. But you end up with some very large expressions. So you can see this is one of the entries in that intermediate T matrix is going to have a lot of additions and multiplications in it. So this is a very large code file. The sparse matrix libraries allow you to write some higher level code, but they start using dynamic memory allocation. So I'm just showing the multiplication as done using the Sparse library, but the Eigen implementation is very similar. So you get these nice high level functions that you're calling, in this case Sparse multiply, and you give it 2 matrices and you get your results back. So it's something that's rather intuitive to write. But we can see that this multiplication step has allocated some memory, and that memory needs to be freed later on. So this is really the telltale sign that we're using dynamic memory allocation here, because if I didn't free these, then the program would have a memory leak. And finally, there's the symbolic multiplication. So it looks like the unrolled loops, but the lines are much shorter. And this is because the elements that we know that are 0 have already been simplified away, because multiplication by 0 just gives you 0, and addition with 0 doesn't change anything. So we can see that in that temporary T matrix, there are the expressions for the entries are much shorter. So this temp variable is the same as the T matrix before. So some of them are just one multiplication. Before you might have seen that there was 800 elements in that temporary matrix. Now there are 501. And that's because we don't have to store the other entries, because they're just going to be 0. So let's see how these algorithms stack up, how these methods stack up when they're actually run on a computer. So when you look at the runtime, we see that the triple for loop is about 12 times slower than the symbolic method. So that's a huge speed increase. So our customers were very happy with that result. The unrolled for loops are faster than the triple for loop because we've gotten rid of that overhead, but it's not a lot faster because it's still doing a lot of useless calculations. And by useless, I mean it's multiplying numbers by 0 and it's adding 0 to numbers. So those are completely useless floating point operations that won't change the result. The eigen and C-sparse libraries are faster than the for loop ones, but you can see that they're not as fast as the symbolic ones. And this is because with the eigen and C-sparse libraries, there's a lot of overhead involved in tracking which elements are 0 and which elements are non-zero. So they just can't be as fast as that symbolically specialized code. If we look at peak memory usage, we see that overall there's not a huge difference between the methods. The one exception being eigen, and this must be just because of how some of the intermediate steps are represented in eigen. But in the end, they all have to store that dense final matrix. So it makes sense that for memory usage wise, they're not too far off from one another. But again, we can see the dynamic memory allocation that's being used because eigen and C-sparse are allocating memory on the heap, whereas the other methods are only using memory on the stack. So that's really important for some embedded system applications, for example, where you might not have access to dynamic memory allocation. So eigen and C-sparse are just ruled out as possibilities straight from the beginning. The last metric is the compiled object file sizes. So the triple for loop was something that you would see in a numeric library, and the eigen and C-sparse were sparse matrix libraries. So they all have a very small code size because the code is very small, but it's very generic. So those are just tiny numbers. But for the unrolled for loops and the symbolic code, you have much larger code file sizes, and so much larger object file sizes. The unrolled one is sitting around a megabyte, whereas the symbolic is around 190K. So this is the one disadvantage to the symbolic methods, is that you do need to have a larger code file size. And that will also mean a larger compile time. So really what specialization offers you here is a design trade-off. And it's a trade-off between execution speed and code size. So what we have is that for a lot of our customers in the scenarios that they're facing, storage is cheap, but time is tight. So this is a trade-off that they're often very happy with. And Maple's symbolic capabilities help you transfer that equation-level knowledge that you had when you were originally defining your problem all the way down to generating optimized code. So those steps that you always had to do manually before, you can start automating parts of that, and you can start getting more efficient solutions as a result. So if you have any more questions about this, I encourage you to contact us through our website, and I hope you learned something about symbolic specialization today. Thank you.